So I want to show you an example of the kinds of things that go wrong when people attempt to use one-time pads in practice. And this is a story that is very important to the history of computing, as well as the history of the world. And it's how the Allies at Bletchley Park were able to break the Lorenz cipher, which was a cipher used by the Nazis to communicate between the capitals of the cities of Europe. This story goes back at least to the 1919 patent that Gilbert Vernam, who was an engineer working at Bell Labs, got on a one-time pad system. It shouldn't really be called a one-time pad. It was a reuse pad system. And the idea behind this is somewhat clear from the patent, especially if we rotate it so we can see it more clearly. So one thing you can see is that there are 5 wires going into it. And this is the output from reading a tape that encodes the message. The key was also on a paper tape. And the encoding used just 5 bits. So this was the Baudot code. With 5 bits, we can encode 32 different symbols. So that's enough for the alphabet and a few punctuation marks. And you can see the letters were encoded. There's the strip down the middle that was used to align the tape. And then there are 5 bits to encode each letter. Managing paper tapes like this was difficult, and the keys needed to be distributed on paper tapes. If the keys were constructed in a perfectly random way, and you had enough key that you never need to reuse it, well, this would actually be a perfect cipher. This would be a perfectly good one-time pad. Problem is, distributing large paper tapes is pretty difficult, especially if you're trying to do this in wartime. So the machine that was built based around the same idea as the Lorenz cipher machine, where instead of having a paper tape with the key, you had a machine that would attempt to produce a good sequence of key bits. And of course, it's impossible for a machine to produce a perfectly random sequence. The structure of the machine determines properties of the sequence that's produced. So the machine would generate a key sequence based on its configuration. And that configuration is the initial settings of all the rotors and other parameters that we'll talk about soon. If there are 2 machines that start in the same configuration, say one in Berlin and one in Paris, well, then they produce the same key. Their encryption is just the message XORed with the key. That produces the ciphertext. That's sent over radio wireless, received at the other end, which puts it into a machine starting with the same configuration. So that means that ciphertext XORed with the key generated by this machine starting from the same configuration will decrypt to receive the message. The machine was designed to produce a large number of possible sequences. There are a lot of complex operations, which we'll talk about a little next. But the key would not repeat for 10 to the 19 letters. So given that this number was larger than the amount of text written by humans, at least at the time, this led the Nazis using it to believe that it provided the highest security they needed. They also were confident that because these machines operated in capitals, they weren't like the Enigma machines, which operated in the field, that they never lost one of these machines, that the Allies never actually had access to the actual machine to try to figure out how it worked.